Okay, so this is going to be the second movie on, or the second lecture on Laplace transforms. I'm doing it very quickly after the first one. I've got a lot of assignments, particularly from you guys, that I've got to mark next week. So it's probably only going to be one lecture next week rather than two. But we'll see how we get on. Right, so what I wanted to do was go over those a couple of questions from that worksheet that I gave you at the end of last time. So it was these 4 questions here, 1, 2, 3, and I'm going to go over questions 1 and 2, or give you the answers to them. I gave the answers already, but how I got there. Right, so I wrote down the function f of t is t cubed, take away t squared plus 5t plus 2. Now I'm wanting to take the Laplace transform of everything, so it's a Laplace transform of t cubed, Laplace transform of t squared. That 5 is just a constant, which is a number. It's a 5, not a s. Right. It's a 5 from there. And then I've got to find the Laplace transform of 2 as well. So I've worked on my Laplace transform from the table, Laplace transform from the table, Laplace transform from the table, and the Laplace transform from the table. Right, and I've ended up with this thing here. Now excuse the multiply by 1, multiply by s. Right, that's been done later. So I've got 6 over s to the power of 4, take away 2 over s cubed, plus 5 over s squared, plus 2 over s. Now, as I've said, you want to make it one fraction if you possibly can. So what I've done is created a common denominator, which is s to the power of 4. So I've multiplied the bottom and top by both 1 there, because it's already s to the power of 4. And I need to make it s to the power of 4, so I need to multiply top and bottom by s. Same here, multiply top and bottom by s squared. And here multiply top and bottom by s cubed. That's a wee cube there. Couldn't quite fit it in the paper. Right, so that means I'm left with this thing here. 6 over s to the power of 4, take away 2 over s to the power of 4, plus 5s squared over s to the power of 4, plus 2s cubed over s to the power of 4. And I've just simply rewritten it around with the highest power letter term at the front. And that's exactly the same as the answer I gave you in the answer sheet. So all they've done is created one fraction, where in my examples I left it as 4 separate fractions. They're both right, but when we're doing Laplace transforms, they mostly prefer one single fraction. Right, example 2 was a lot easier. So, as usual, take the Laplace transform of both parts. I'm left with that fraction and that fraction. And luckily enough, the denominator is the same, so I can just put the 2 top bits together. Right, now what I want to do now is go on and talk a little bit more about some more Laplace transforms, and then eventually go into inverse Laplace transforms today. Because I want to try and get half of Laplace done today, or over the course of this week, and so we can finish it off over the next 2 weeks. Right, it's a lot to do, it's a lot of theory in it, but hopefully it will be okay. So let's look at first the first shift theorem. And if you look at this in a book or the notes, it looks so complicated. Right? The first shift theorem looks so complicated, right? This is what it says here. If f of t is a function having a Laplace transform fs, then the function e to the power of at times f of t has a Laplace transform given by capital F of s take away a. Sometimes f s take away a is denoted by, right, that there is impossible to make head nor tail from, right? So what I'm going to do is I'm going to boil it down where I can into proper or normal English where I can, and then give you a few examples. It's a lot easier than this terminology would have you believe, right? Okay, so this is used when you have an exponential containing t as a power multiplying another function you can Laplace transform. Right, so all the first shift theorem's saying is if I have effectively an exponential multiplying something else, so kind of like a product rule as you would see in differentiation, right? So here's a couple of examples where you would know to use the first shift theorem. So if I had t to the power of 4 e to the power of negative 3t. Right, so you can see I've got an exponential with t in it, right? And that's multiplying something else I can find the Laplace transform of. So I would use first shift theorem because it's an exponential term multiplying another term that you can find the Laplace transform of. Right, another one. I'll just write one slightly differently. Again, what I've got is I've got an exponential with t multiplying another function with t that I can find the Laplace transform. So in both of those cases, I would need to use the first shift theorem. And it's actually really useful, the first shift theorem. Right, now here's our rule. And this is going to look a little bit technical, but it's not, right? When we actually come to use it, it's not a problem at all, right? So if I've got an exponential multiplying another function I can Laplace transform, right? So that just looks like this thing here. An exponential with t multiplying another function I can Laplace transform, right? Okay. So if I want to Laplace transform that, right, I get the Laplace transform as s goes to s take away a. So that means the Laplace transform as s becomes s take away. So effectively what's going to happen is whatever the number is here, we write as s goes to s take away that number. So we just find the Laplace transform of this bit here, and then we write this extra little bit here. Okay, and remember that just means find the Laplace transform of that ft part. Right. Again, to me, if I was you guys, I would still think it sounds too technical. So let's do a couple of examples, right? Find right, so that just means find the Laplace transform, remember, right? So f of t equals t squared e to the power of negative 40. Right, so I want to find the Laplace transform f of t. Right, now, so I can see it's an exponential multiplying something that I can normally Laplace transform using my table that I've got here in page number 18 of my booklet. So t squared would mean I would use this one here, right? So So I find the Laplace transform of the bit not containing the e, right? Now, effectively the exponential term becomes a set of square brackets, right? And we write as s goes to s take away negative 4. Because remember the rule was is s goes to s take away a when a is positive, so that means it's take away negative 4, right? So, and then in the brackets we do the Laplace transform of this normally. So that's 2 factorial over s cubed. Right. So f of s is 2 over s cubed as s becomes s plus 4. Right, that should be subscript, right? So it should be down, it should be a wee bit smaller than that. That's just, I'm trying not to make my writing too bad today, right? Now, what we do is, this means that we swap all s terms for s plus 4, right? Right, and as soon as we've worked out what that means, the square brackets fall away. Right, and all our s's become s plus 4. So where we had s in the past, we put s plus 4 in its place. Okay, so the square brackets and this bit here sorts out our exponential term. Inside the brackets we find the Laplace transform of the other part of our function. Then we simplify everything down and we substitute in our s plus 4. Example 2. Find fs. Right, so let's try f of t equals e to the power of negative 2t cos 5t. Right, so I want to find the Laplace transform of f of t, because that's what f of s means. So right, now it's an exponential multiplying another term that I can Laplace transform, because I've got a Laplace transform for cos at on my formula sheet. So the exponential becomes the square bracket because of the first shift theorem. And s is becoming s take away whatever the coefficient of t is here. So that's s take away negative 2 again. Now, you could just write s plus 2 there if you want. Now, inside the bracket, we find the Laplace transform of cos 5t. So cos at is s over s squared plus a squared. So cos 5t is going to be s over s squared plus 5 squared. Now, as I said to you before, you're going to have to find a way of being able to write s's and 5's differently, right? But I'm sure you'll find a way that I can read. Right, now, all we then do is, remember that just means s plus 4. You swap all your s's for s plus 4 in the square brackets go away. So I've got s there and an s there. So that s at the top becomes s plus 4. And the s at the bottom becomes s plus 4. like that. Oh, sorry, it's 2. Reach it, s plus 2. That's my fault for not reading. Now, if you want, you could sort all that stuff out in the bottom of the fraction, but I'm not too bothered just now. Right? Doesn't really bother me. I'd probably just leave it as if it was me doing the question. Probably how I would leave it. But if you look at the back of the book, there's probably a whole lot of different things to do. Right. Questions. I would like you to try and find the Laplace transform of 1. Sorry, I'm moving the page up a little bit. Right, so for each of those, can you please move up a little bit? Can you pause the video and using the first shift theorem and the table from your book, can you please answer those questions? So please pause the video now. Right, okay, so the answer to this one here is 4 over s plus 2 squared. Right. I'd expect you to do working for these. I'm just putting these down so that you've got something to, so you know if your answers are right or not. Like that. And that last one there should cause you quite a lot of difficulty. But hopefully if you try those 4 questions, you're going to get a grasp of the first shift theorem. Right, now this is when we start to get a little bit more difficult. Again, it's, as I've always said with maths doesn't get any more difficult, there's just more steps, right? The basics are always the same. Like inverse Laplace transforms. So this is again is going to start with a little bit of theory. Now, inverse, as we know in maths, just means the opposite. So we're just going to be doing the opposite. So if the Laplace transform of f of t is something called capital Fs, then if I have capital Fs and I take the inverse Laplace transform, I end up with f of t back. So that's the normal Laplace transform, that's the inverse Laplace transform. Okay, don't get the two mixed up. You can tell something's been Laplace transformed already if it's fs. You can tell if something hasn't been Laplace transformed if it's t or x or whatever. Now, to do this, we are going to use the table on page number 18 in the opposite way. Right, so hopefully we're going to be able to get a grip to this. Now, but again, this is just about making decisions. Examples, and for all these examples I'm going to get you to find. Right, so f of s equals 1 over s to the power of negative 4. Or sorry, f of s equals 1 over s take away 4. So I need to find the inverse Laplace transform, capital Fs. So that means I need to find the inverse Laplace transform of 1 over s take away 4. Right. So I know the inverse Laplace transform just becomes the normal function with a t in it. Right. So this left hand side, just get used to doing the opposite of what we did when it was a normal Laplace transform. Right. So I'm going to get my table out. Right. So I've got 1 over s take away 4. So which one of these things in the Laplace transform book looks like 1 over s take away something or 1 over s plus something? This one here, 1 over s take away k, where k down there just becomes the coefficient in front of the t. Okay? So that means that just becomes e to the power of 4t. Yeah, let's look at an example 2. Right. Right. Let's have a look at this one. So again, I want to find f of t, so that means I need to find the inverse Laplace transform of f of s. Right. So have a wee look at what your function looks like, right? And it's all to do with the denominator normally, right? The denominator tells you what you should really go to, right? So let's have a look. So I want this thing to look exactly like something in my book, right? So if I look at my book, right, remember I've got 1 over s squared take away 4 squared, right? Oh, sorry, 1 over s squared take away 4. Right, that doesn't have like anything in the bottom alongside the s. That doesn't have anything in the bottom alongside the s. That doesn't have anything in the bottom alongside the s. That does, but it's only s, not s squared, right? My function's got s squared in it, right? So that's got s squared in it and a number in it. That's got s squared in it and a number in it. So it's either this one here or this one here, right? Then I have a look. Does my function have an s on the top? Remember, s is the most important letter in this. Does it have an s in the top? No, it doesn't. So if it doesn't have an s in the top, that means it must be sine. Okay? So now this is a little crucial bit. So if I look at my Laplace, in fact I'll write it in a wee table here. So hopefully we can, just like I did with the previous ones. Right, so my function says a sin at is a over s squared plus a squared. Right, that's what the table says. So I've got something that looks like this, and I want to go that way, right? Because I go the opposite way in the table, right? So I need this thing in the bottom to be written as a squared plus a squared. So 4 is 2 squared, so I'm going to rewrite that as s squared plus 2 squared, right? So now the bottom bit's right, but I need those two numbers to be the same. I need that to be a 2. Okay? Now, it's not a 2 just now, it's a 1. So that means I need to manipulate it by a coefficient outside, right? So what multiplied by 2 gives me 1? 1/2. So it's just like those ln integration questions that we did in Engineering 3. Right? So it's a bit like that. So that means that f of t is 1/2 sin 2t, because this thing here becomes sin 2t. Okay, now what I want to do is the last one and then some questions for you today. I'm going to cut this lecture a little bit short. I'm not going to go into more complicated inverse Laplace transforms. I'll do that next week because I think it's a Friday. Let's not stress ourselves too much. Right, so f of s is 16s over s squared plus 4 squared. Right, so again, I need to find the inverse Laplace transform of f of s. Right, so I go down my Laplace transform table, right? Right, and I want something again that's got an s squared on the bottom of it, right? And a number. So this has got an s squared on the bottom of it and a number. This has got an s squared on the bottom of it and a number. But look at my original function. It's also got a bracket with a squared on it. So is there any that look exactly like that? Well, yeah. I've got this one here, which is get s squared plus a number squared squared. So that's s squared plus a number in a bracket squared. And that's s squared plus a number in a bracket squared. So it's either this one here or this one here. Right, so let's write them both into the page. Okay, so looking at the denominator of my function there, I know it's either one of these two because it looks the same. It's got an s squared in it, it's got a bracket, and it's got a squared on the outside of it. Right, now it's got to be that one there because there's no plus something on the top. Right, so I know it's not going to be that one there. Right, so then I need to make the bottom look like that. So let's do that. So that's 16s over s squared plus 2 squared squared. Right? just like we did in the last one, right? So now the bottom looks exactly the same. Just change that to f of t. Right. Now, a is 2. So that needs to be 2 times 2 times s. So the top bit needs to be 4s all over s squared plus 2 squared squared. Because if it does, it matches this exactly. Right? So what multiplied by 4s gives me 16s? 4. Right, so here is going to be t sin at, but our a is 2. So it's t sin 2t. Okay, now the next section involving this involves partial fractions, completing the square, and a whole lot of previous other stuff that we've covered before. So it's a good idea if you can have a look at partial fractions. I'm going to hopefully have enough time to go through it, or I will have enough time to go through it next week. I'm not going to go through any of these questions here, so I don't have time at the minute, or give you any questions on this, but hopefully those notes will be enough, and those questions on the first shift theorem will be enough. So I'll come back next week with all of inverse Laplace transforms. The lecture will probably be about 2 hours worth of lectures. I know this is difficult, but doing it from distance, this is the best we can do. Okay, so have a good weekend.